put all our algorithms into context and better understand them, what we'll do now is go through some basic properties of shortest paths in edge-weighted directed graphs. So what kind of data structures are going to need, first of all? Our goal is to find the shortest path from S to every other vertex. So the first observation is that there's going to be a shortest paths tree solution. Well, if no two paths have the same length, then certainly it's going to be such a solution. And there's a number of ways to convince yourself that there's going to be a tree. If you've got two paths to the same vertex, you can delete the last edge on one of them and keep going until all that's left is a tree, for example. So what we want to do is compute a tree. Now, we've done that in several algorithms before, and a reasonable way to represent the shortest paths tree is to use two vertex indexed arrays. The first one is for every vertex, compute the length of the shortest path from S to that vertex. So in this case, we have this shortest paths tree, and we'll keep the length of the shortest path from the source 0 to each vertex. So 0, 2, the length of that shortest path is 0.26. 0, 2, 7, it's 0.60, and like that. So because you go from 0 to 2, 0.36, and from 2 to 7, 0.34, you get 0.60. And so forth. And then the other thing, as we've done before, is use parent link representation where edge to V is going to be the last edge that takes us to V. And by following back through that array, we can get the path, as we've done several times before. If we want the path from 0 to 6, we go to edge to 6 and says, well, the last thing we do is 3 to 6. Then we go to 3 and say the way we get to 3 is from 7. We go to 7, say the way we get to 7 is from 2. We go to 2 and say that's the way we get to 0. And if we put all those things on a stack, and then we can return them as an iterable to the client, and that gives the edges on the shortest path. So that's the data structures that we're going to use for shortest paths. This is actually the code that does what I just said. The client query, give me the distance, it just returns, uses V to index into the instance array and returns the distance. And if the client asks for the path, then we make a stack, and then we use a variable E, which is a directed edge, and we start at edge 2V, and as long as it's not null, we push it onto the path, and then go to the edge 2 entry for the vertex that we came from, and that gives the vertex that we came from to get to that vertex, and keep going until we run out of vertices, which happens at the source, and then return the path, and that's an iterable that gives the client the path. So that's the implementation of the two query methods. So now what we're going to want to talk about for the rest of the lecture is the algorithms that build these data structures. Now, all of the algorithms that we look at are based on a concept called relaxation, or edge relaxation. So now recall that our data structures, so we're going to talk about relaxing an edge from V to W, and we have an example here from V to W. And at the point that we're going to relax this edge, we'll have our data structures in process, and dis2, we haven't seen all edges, we haven't seen all paths in the intermediate part of some algorithm. So, but we'll try to make sure that dis2V for every vertex is the length of the shortest known path to that vertex. And that's going to be the same for W. So these are all the edges that are in edge2 that we know paths from S to some vertex. So dis2V and dis2W will contain the shortest known paths. Now, if we, also edge 2W and V is the, edge 2W is the last edge and the shortest known path from S to W. The same with edge 2V, of course. Now, so to relax along the edge from V to W, essentially that means let's update the data structures to take that edge into account. And what happens in this case is that the edge gives a better way to get to W. So that's what relaxing is. That edge gives us a new shortest path, so we want to include it in the data structures. So since it has a shorter path, we have to update both dist2W and edge2W. That is, we have a new way to get to W, so we have to throw away that old edge that came to W, and we have a new shorter distance. Instead of 7.2 that came that old way, we have 4.4 that gets us a new way. So edge relaxation is a very natural operation. When we consider a new edge, does it give a new shortest path to that vertex or not? If it doesn't, we ignore it. If it does, we update the data structures to include that edge and forget about the old edge that took us to that vertex. That's edge relaxation. And this is easy implementation of edge relaxation in code. So to relax an edge, we pull out its from and to vertices in V and W according to our standard idiom, and then we just see if the distance to W was the shortest path before is bigger than the distance to V plus the weight of the edge that would take us from V to W. If it's bigger, that means we found a new path. If it's less than or equal, we ignore it. And if we found a new path, we have to update the distance to W to be the new distance to V plus follow VW, and then we have to update edge to W and throw away the old version and say that our new edge from V to W is the best path to W as far as we know. So that's easy code for edge relaxation. Now, we're going to use edge relaxation in a really fundamental way to compute shortest paths. But there's one other important idea, which is called optimality conditions. And this is a way to know that we have shortest paths. We have computed all the shortest paths. So the shortest path optimality conditions is embodied in this proposition. So we have an edge-weighted digraph, and we have the dist2 array. Let's just talk about the distances, and the paths go with the distances. But the key point is that the dist2 array represents shortest path distances from the given source S, if and only if these two conditions hold. So the first thing is, if it's the length for every vertex, dist2V is the length of some path from S to the vertex, and our algorithms will always ensure that. And then the second thing is for every edge VW, we have this condition that the dist2W that we have stored is less than or equal to dist2V plus the weight of the edge from V to W. That's the shortest path optimality conditions. If they're equal, so sometimes they'll be equal, for example, if VW is the last edge on the shortest path, and sometimes they'll be greater, but it'll never be smaller. There'll never be a way to get to W that we haven't found. That's the shortest path optimality conditions. And again, just a quick proof, although the best way to understand proofs is to read them slowly, not listen to them spoken quickly, but I'll quickly outline them. So here's the necessary. Suppose that, so we want to prove that if this is true, then we have shortest path. So to do that, we assume the contrary. Suppose that the distance to W is bigger than the distance to V plus E dot weight for some edge, then that path is going to give a path to W that's shorter than distance W, because V is a path and the weight's shorter, and that is a contradiction to the idea that you have shortest paths, so there can't be any such edge where that condition holds. So that's necessary. And then sufficient, suppose that we have a shortest path from S to W, then we're assuming these conditions all hold, then for every edge on the path, this has to all hold. So it starts at the end. So the distance to the last edge goes from VK minus 1 to VK. So distance to VK is less than or equal to the distance to VK minus 1 plus the weight of the kth edge. And so just continuing down that way, then from the source to the first edge, so source plus the weight of the first edge is greater or equal distance to the first vertex after the source, and all those conditions have to hold. And then what we can do is just add up all those weights and simplify it. And then that shows that the distance to W is equal to the length of the shortest path. And so it's got to be the weight of the shortest path, because it's the weight of some path and it's got that weight. It's got to be the weight of the shortest path. So if those conditions hold, we have shortest paths. So the point of this proof, it's a slightly complicated proof, but it's not too bad. It's quite natural. Is that all we have to know to check that we have computed shortest paths is that these optimality conditions hold. To prove that an algorithm computes shortest paths, we just have to prove that it ends up with the optimality conditions in force. And that's what we'll be doing. And the optimality condition really is just saying there's no edge there that we missed. Okay, so with that idea, in fact, there's a very simple, easy to state, generic algorithm that is going to compute shortest paths. And it's very simple. We start with the distance to the source being 0 and the distance to every other vertex infinity. And all we do is repeat until the optimality conditions are satisfied, relax any edge. Just go ahead and relax edges until the optimality conditions are satisfied. So that's a very general algorithm. We don't say how to decide which edge to relax or how to know the optimality conditions are satisfied. But still, it's quite an amazingly simple generic algorithm. So how do we know, how can we show that it computes the SPT? Well, it's pretty simple. Throughout the algorithm, we're making sure that, because of the way that we do relax edges, the distance to V is the length of a simple path from S to V, and the edge to V is the last edge on that path. That's what relaxation does for any vertex that we touch. And not only that, every relaxation that succeeds decreases the distances. And we've assumed that there's a way to get to every vertex, and there's only a finite number of paths, so it can decrease at most a finite number of times. So it's going to the algorithm's going to terminate. It's as simple as that. Again, this is a little bit of a mind-blowing concept, but we'll leave that for more careful study, and just for now realize that all we have to do is relax along edges. And what we're going to do now is look at different ways of figuring out how to choose which edge to relax. The first algorithm that we'll look at is a classic algorithm known as Dijkstra's algorithm, one of the most famous of all algorithms. And that is effective when the weights are non-negative. Then we'll look at an algorithm that works even with negative weights as long as there aren't any directed cycles. And then we'll look at an even older algorithm than Dijkstra's, the Bellman-Ford algorithm, that can solve the shortest path problem in graphs with negative weights as long as there's no negative cycles.